That's from what I've heard. That's true.
Any material, both notes and that's how
And it's also like,
Dr. Briggs, his calculates hard enough. It's very accurate. Like the stuff you learn. It's good enough. He makes it not easy.
Yeah, I love Dr. Briggs. I had him for Calc 1, 2, and 3. I love him. He's really good.
But he doesn't teach classes.
I was disappointed about that too. I talked to him. I had like 2 choices for PQ.
No one is online today. Everybody's in class today. So you had exam or something? Very heated argument about exam and stuff. How was the Aero exam?
That was good.
Well, of course, you're not going to say anything negative about it.
The minimum is perfection.
Okay, so let's begin with I know you, don't worry.
Did you get the letter I left in your?
Yeah, thank you very much. So, you're not supposed, you're supposed to bring also laptop too. He wants me to set up laptop.
Oh, I don't know if he has it yet.
Yeah, he bought a new laptop and he wants me to set up everything.
Yeah, I can bring it.
Email.
Yeah, when he gets it, I don't think he has it yet.
Yeah, that's right. He said he ordered.
Yeah.
Oh, yeah, that's kind of what it is. To get to.
Actually, I'm kind of getting doubtful about what I'm doing, and there's no one really wants this one.
Do they even collect it for you? They do?
Well, basically requires me to take attendance, and then I'm not gonna sacrifice like 5 minutes every class taking attendance and calling names. So I basically did video.
That's what I got.
Seems like no one needs it.
So he does kind of keep track of our attendance.
I'm not even sure if they they're tracking attendance. They're just announcing some kind of fake news all the time. So anyways, I'll do what I used to be doing, but don't worry too much about this thing. Okay. Everybody's in class. All right. So let's begin with updates. There's one new update here. Okay. Looks like Monday next week you have to turn in project phase 1. Hopefully you're working on it. Okay. Let me show you my code. What's that? I keep forgetting about it. So I'm gonna run MATLAB. Okay. And then I'm gonna show you what I'm doing so that your team can sort of modify if you're doing something wrong. So this is Aerodynamic project phase 1. So as you can see, I'm coding everything in TypeScript. It's totally different from you, so you cannot copy it. Anyways, satellite.mlx, this is TypeScript. Okay. So this is how I code it. And I'm going to undock the command window and show you side by side with vibe script. This computer is so damn slow. Anyways, okay. So this is command window. This is vibe script side by side. So when you run vibe script, basically command window says enter selection. The selection is Mercury, Venus, Earth. Okay, so Mercury, Venus, Earth, Moon, Mars, Jupiter, Saturn, blah, blah, blah. Okay, yeah, so I'm going to choose something, maybe Earth, EA, hit enter. Next, okay, so what is the mass? I don't know, 5,000. What is the unit? Unit could be, what is units around? Kilogram slag or pound mass, okay? So I'm going to enter a kilogram. And then satellite altitude is, I don't know, it could be 7,000. I can put in feet. I can intentionally mix up those two units. I can do that because it's computer. And then 7,000 feet is low. All right. That's really low. 7,000 feet? No, it's not satellite. I'm sorry. Well, kilometers, okay. Sorry, 7,000 kilometers. I'll stick with this unit. Then you compute gravitational force is this much Newton or this much kilogram force or this much pound force. I compute all three units. So you are going to go through a series of inputs, right? You keep asking users type in units and then numbers. What is it? First of all, select your planet. Number two is like what is the mass number? Is that the kilogram or slag or pound mass? The next is, okay, so what is the altitude and number? Is that the kilometer or feet? Then you're going to compute gravitational force in Newton, kilogram force, and pound force. That's what I'm doing. Okay? So that's something I expect. Okay, go ahead.
So would we be allowed to just convert, if we get it in feet, can we convert it to kilometers and then just solve everything in newtons?
I think something that's, okay, what I'm doing is, I think, let me understand what I'm doing. So what I'm doing is choose your planet, input mass, load planetary data. Yeah. Planetary data times mass convert. What units am I using? I'm not sure. Mass is input, display, blah, blah, blah. Input is unit, format, spec, everything. So if the unit is in slag, I convert it to kilogram, looks like, yeah.
So you converted to SI and then did all your conversions in SI?
Probably. I try to remember because I did it a long time. So if the unit is pound mass, I convert it to, yeah, kilogram. Yeah, I'm using SI unit in my computation. So if the user type in like a non-SI unit, I convert it to SI. And they use SI in computation. Looks like you can do that. Or you can faithfully choose any unit, and each time you get a unit, use that unit system to compute. You can definitely do that. Well, computer can do. Any other question? Go ahead.
For the pressure, density, and temperature.
Which
part.
which one? This is pressure, density, temperature.
No, for the task.
The other
two.
one. The other one. Okay. So any other question for this one? All right, good. So let's take a look at the other one. So the other one is standard ADM. Looks like. Okay. So this is how I run it. Okay. Let me run this. Standard APM, let me just clear. So suppose if I run this code, what happens is input is a geometric altitude. So let's say 90 kilometers, 90 kilometers. pretty high altitude. And then you're going to compute temperature, Kelvin, Rankine, pressure in Pascal, PSF, and density, kilogram per cubic meter, and stress per cubic foot. That's what I'm doing. And then at the same time, I'm actually converting it to geopotential. Yeah. So this is geopotential corresponding to 90 kilometer geometric is 88.746 kilometer geopotential. So what's your question?
So do you want us to give our pressure, density, and temperature in both SI and US custom made?
That's what I'm doing here, yes.
Or
That's what I'm doing.
On mine, I have it specified before, and then it only gives you those answers.
As long as I can follow through and then understand, I give you full credit. But if you confuse me, you don't get credit. This is what I'm doing. So it's probably safer to stick with what I'm doing. But as long as I understand your code and can properly use it without errors, I give you credit. In other words, do you satisfy the requirement of the documentation? That's the big question. If not, you don't get the credit. Any other question?
Do you require our code to be commented?
Huh?
Do you require our code to be commented? Like to have comments for like, well, this part does
Not really.
this. Okay.
Because do you think I look into the code?
I
If
don't
it
know.
doesn't run,
I
it
don't
doesn't
know.
run. If
Some-
it
some-
doesn't run, it doesn't run. I
Some
give you
professors
zero.
look, some professors don't.
Well, if I teach MATLAB, yes. This is not MATLAB.
Fair enough.
I'm teaching MATLAB, seriously.
Yeah.
I'm seriously picky for those freshmen.
Right.
If they don't put the comments, I take points off. If they don't put the header, I take points off. If they don't get section break, I take points off. I take points off for everything. They hate me. But I don't care. Because they need to be trained up. You're not. You mastered MATLAB already. I don't have to look into your code. If your code doesn't run, it doesn't run. I don't even look at it. You get zero. This is no MATLAB question. So anyways, you're not going to submit the code which doesn't run at all, right? Freshmen do. Believe me or not, they submit code, it doesn't run at all. I have to take a look at it. Okay, well, so what's causing this error? Did you even check it? Well, wait a minute, this is syntax terrible. How many partial credit should I give? Because zero is too harsh for freshmen, right? So again, I teach different ways. I mean, this is not MATLAB class. I don't think you need a comment as long as your team understand each other. But without comment, it's kind of difficult, right? Because this is teamwork. So teamwork is always in place. So you need to be nice against your teams. If you code your code, you are the only one who can understand this code can code. It's not teamwork. The team hates you. So again, it's natural selection process. You're already there. So I don't have to take care of your MATLAB skill sets. I assume you already have it. Anyways, any other questions? But again, this is my code. I always have header, comments, and space, and section breaks, of course. That's a common sense. If other teachers don't teach you that kind of stuff, too bad. It's not my problem. It's that other teacher's problem. I'm picky on coding. Anyways, it's partially because I'm Japanese. Too bad. I hate to say that. Toyota engineer in Japan. Oh yeah, this is the style. I can accept from freshmen. Freshmen don't do it. They open up MATLAB and type in stuff, and no one can understand but you kind of code, and they submit half checked. It doesn't run, give you error. Hey, I need a partial credit for what? Well, I give you, I don't know, 2 out of 10. Oh, why is it so? Oh, because it's a piece of. Anyways, question.
I don't know if you said this, but what did you do before you teach?
What did I do?
Yeah.
Before I teach? I studied, of course, at the school. I got
did you
PhD.
ever do like a job?
Well, I worked 7 years at the Toyota in Japan. I'm automotive. You didn't know that? I always, I thought I said it on day
Yeah,
one.
you did.
I think I did. Right?
It's been a couple weeks. We just
Look,
can't
keep it
remember.
up.
It's been more than
Anyways,
five
any
minutes.
question about this MATLAB code? Straightforward. you can check against the standard table, of course. Your computed result should be almost one-on-one with the standard table of atmosphere, right? You should check that. The other one, gravitational acceleration, of course, you can do hand calculation, check against. Okay. So hopefully you can do this by Monday. This is easy. I mean, the whole purpose of this phase 1 project is hopefully you form a good team and work together for project 2. A and B, those are the real projects. This is fake project. I just made up out of cut paste from EGR class. Okay? So if you cannot code this kind of thing, shame on you. This is EGR content. 115. You took it already when you were freshman. Okay? So this is piece of cake code. You probably need one day. Rest of one. Okay? You have a skill. Okay, so today we are going to finish up we're going to finish up A5, okay? And then hopefully get some questions if you have some questions of unit B1, which is YouTube lecture, and then we get into B2. Okay, so unit A5, we introduced you the coefficients of aerodynamics, and then of course you know, since you worked on quiz 6, why do we need to work on coefficients? Everything is dimensionless, of course. We're not going to talk anything comes with dimensions. The reason is, oftentimes we test something in small scale to predict larger scale performance, which requires similitude. Okay? So please properly understand why people use Reynolds number, not the airspeed. You need to understand people use Mach number, and then you have to understand they don't talk about drag, they talk about drag coefficient. Okay, not the lift coefficient. It's not location. It's a percent location from the code, kind of thing, from the leading edge of the code. So everything doesn't have any dimensions in it. There's a reason for it. We have to make it independent to the size. So today we talk about aerodynamic center instead of center of pressure. Why do we need such a thing? Anybody, please summarize what we did in last class. Why do we need aerodynamic center? Go ahead.
The center of pressure depends on, center of pressure depends on angle of attack. The aerodynamic center doesn't.
Aerodynamic center doesn't. Aerodynamic center is a fixed position depending on the cross section, and it's almost always quote-unquote. Okay, so we want a fixed reference point where you're going to put your resultant force, in this case, which is lift. In other words, this is a resultant, okay? You can put the resultant force in anywhere along the code. It's your freedom. In other words, when you pitch up and pitch down an airplane, creates the lift and drag moment, okay, which is not the single point value. In other words, this is a resultant you're talking about. Pressure is distributed over the surface. As a result, you're going to create a force in this direction, force in that direction, rotating around certain fixed point. That is what we are talking about. So you can place lift in any location if you want to. Then if you want to put the lift, hopefully that is the fixed point. Because that's where the lift is generated. Suppose airplane center of gravity is around here. Okay? If you increase the angle of attack, lift is increased. That is going to create a pitch up tendency or something like that around the center of gravity. That is going to be the control mechanism of your airplane. So you have to somehow analyze how you control your airplane as a flight mechanics. So we are going to use always aerodynamic center as the position where the lift is acting through. This is the resultant out of the pressure distribution of the surface. Okay. So, anyways, what is the class you need to remember for doing this? Statics. Here we go. Okay. So I don't want to deal with your statics knowledge or skill set. If you don't have it, I guess you shouldn't be here. Statics is all about, I'm talking about here. Okay? So now, we are going to do the exact same practice here. We did the same practice in the previous class. I have two models of airfoil. Airfoil where you place your lift and drag at aerodynamic center location right here, measured from leading edge. This is aerodynamic center, XAC. And then you happen to put lift and drag, well, drag is missing, but anyways, drag doesn't do anything, but let me just add, sorry. Drag is acting here too. It probably doesn't mean much, but drag here. So lift and drag placed in quarter code. Obviously, you're going to expect quarter code moment per unit span developed at the quarter code. Okay, so those two are, again, equivalent. Okay, now first of all, let's define what is the aerodynamic center. So this is the formal definition. What is this location anyways? Now, do you remember the definition of center of pressure on the previous page? So let's begin with that. Center of pressure, what is the definition? What kind of location is that? So as I define center of pressure, this is the location, location, of course, along a given code of an airfoil. In this case, I'm going to limit my discussion for airfoil. Now, we are going to talk about wing. If we talk about wing, you have to come up with what is the average code, mean aerodynamic code. You have to find out those things. Okay. But anyways, this is airfoil. So cross section is constant, and then it's a unit span of a constant cross section. Anyways, that's airfoil. So the location along a given code of an airfoil where pitching moment is 0. That's what it is, right? This is quite important formal definition of center of pressure. So mathematically speaking, you can say moment per unit span taken at the center of pressure. What is it? Good. And then if you convert it to cm center of pressure, what is it? Also 0. So this is the definition of center of pressure. However, the problem is this actually moves back and forth with respect to the angle of attack. So it's not the fixed position. So we cannot really use it as a reference point. So aerodynamic center, the desire we have here is, hopefully this is fixed location. Aerodynamic center. Now, by the way, aerodynamic center of actual 3D airplane is called the neutral point. It's a different word, but it's the same meaning. Neutral point. Okay. If the neutral point is forward of the center of gravity, does it make airplane stable or unstable?
Unstable.
Unstable. That's right. So how much distance apart between neutral point to the center of gravity is essentially static motion, SM. So that's something you have to design for your actual airplane. Okay. This is actually aerodynamics class. We're not going to cover those things, but it's a flight mechanics contents. Okay. We talk a little bit about it, not so much. So what is the aerodynamic center? This is the location, once again, along a given code of an airfoil where pitching moment becomes independent of angle of attack. This is the location, fixed point. In other words, this is the location that if you pitch up or pitch down and changing lift coefficients, okay, but the moment doesn't change at that point. Mathematically speaking, if you take a moment at aerodynamic center, what's this? some kind of constant. Okay, because moment doesn't change. That means if you take moment coefficient taken at aerodynamic center, that is constant. This is quite an important definition of aerodynamic center. Please remember that. Now, important thing is, I'm saying this is constant, right? This constant could possibly be 0. 0 is also one of the constants. Okay, so is there any possibility that aerodynamic center could also be center of pressure? Yeah, it's possible. We are going to see those kind of cases later by looking at the real data set of 1950s. Okay, so those are the very important differences between center of pressure and aerodynamic center. I think I can almost guarantee this is going to be on the exam. Okay. If you don't know this kind of thing, I'm not going to pass you. This is very fundamentals of aerodynamics. If you don't know this, you shouldn't design airplane. Okay, so let's move on. We're going to find out location of the aerodynamic center in the very exact same way that we did in last class. Let's take a look at the left figure and right figure. Okay, go ahead, question.
Yeah, that CM is center of mass, right?
Huh?
The CM.
What? What are you talking about? This is a moment coefficient.
Okay.
At the aerodynamic center, this is a moment coefficient of center of pressure.
Oh.
If you're talking about center of mass, is that center of mass you're talking about?
Yeah.
Center of mass is usually CM capital, center of mass. But we're not going to use center of mass for airplane, you know that? Center of gravity we use. Center of mass probably doesn't show up in here. I think. Anyways, let's move on. Any other question? But actually, I appreciate that kind of question. Basically, sanity check. You're completely off the tangent. Kind of thing. Okay. CM is moment coefficient. Okay. So let's do the exact same thing. You're going to take a look at right figure and left figure. What did we do in last class? We checked how much moment is developed at leading edge, right? So left figure, what kind of moment you expect? Of course, already have moment developed at the aerodynamic center, M prime AC plus or minus which one? Minus XAC times L prime is going to give you pitch down moment. So those two things added together is going to be total moment developed at the leading edge, right? So we are going to do the same thing. So, okay. So it's the exact same thing. Considering you're going to talk about the moment developed. It could be any location, but I choose like a leading edge because it's so convenient. Developed at the leading edge. Okay. So left figure. It's basically left figure as M prime AC. This is aerodynamic center moment per unit span developed already. This is positive pitch up moment. And then lift is going to create the pitch down moment. So this is going to be minus XAC times L prime, right? So those two added together is going to be the total moment developed at the leading edge on left figure, which can be equal to the right figure. Let's take a look at right figure once again. Zoom out. So right figure here, obviously the same thing, moment at the quarter foot per unit span, and then this lift create the pitch down moment. So it's kind of similarly, you can say that moment at the quarter foot per unit span minus quarter code times lift per unit span. Do you follow that? Okay. So let's replace this XAC, okay, XAC. So XAC, let me just zoom in a little bit. XAC is equal to code length times X over bar AC. Do you follow that? X over bar is equal to X over C in general. X over bar is a normalized coordinate as we introduced here in last class. So I can express XAC by code length multiplied by X over bar AC. Do you follow?
Yeah.
Okay, let's do that. And so now, you can say M prime AC minus, this is C times X over bar AC times L prime, which is equal to M prime quarter code minus quarter code times L prime. And then you're going to solve this for M prime AC. Okay. So this is aerodynamic center moment per unit spin, which is equal to lift per unit spin multiplied by code length times XAC over bar minus C over 4 plus M prime quarter code. Okay, so far? Next, okay, I want to do some, I don't know, what's that? I'm going to massage this equation. I shouldn't use that kind of word, but anyways, my old math professor said, oh, let's massage this equation. What do you mean massage? But anyways, you're going to divide by Q infinity C squared for both sides. Let's do that. Okay. So if you do such a thing, I'm going to change it to green. So you are going to have left-hand side is M prime AC divided by Q infinity C squared. Okay, I'm dividing by Q infinity C squared, which is equal to, this is going to be L prime divided by Q infinity C. One of the C cancels out this C, so this is going to be X over bar AC minus 1 over 4, okay? So one of the C code lengths is going to divide through this code and then this code, right, already, okay? So plus, this is M prime quarter code divided by Q infinity C square, and then you probably stop and think, wait a second, what the heck is this? And what is that? And what is this? Anybody? This is what?
Moment coefficient.
Cm at AC, right? Okay. What is this?
Lift coefficient.
Lift coefficient, CL. What is this?
Moment coefficient, of course.
Cm at quarter code. What, Robert?
Sorry, isn't it better to just put the C in the
Huh?
X bar AC and
Huh?
C over 4? Because you,
Huh?
you haven't distributed yet.
Huh?
Does that make sense?
No. You are dividing both sides by Q
Yeah.
infinity C square. This is Q infinity C, but the other C is already canceling out this C and this C. Right?
Yes.
Yeah.
Yeah.
Yeah. Does it make sense?
It
Does
does.
it? Does it? Okay. I hope so. I'm kind of cutting through one line, but anyways, I hope you understand.
Yeah.
Okay. Okay. So this is equation-wise. This is Cm aerodynamic center, which is CL times X over bar AC minus 0.25. That's 1/4 plus Cm quarter code. Okay. Now, next thing is I want to do one more. From this equation, I want to differentiate. You have a logic reaction for differentiate?
Yes.
Well, differentiate means, okay, you're going to basically chop down into small segments to see how it behaves. That's differentiation. Integration is opposite. Small tiny pieces, just piece together what kind of things you can actually create out of it. So if you start thinking about physically, not the mathematical sense, you probably don't have biologic reaction because it makes more physical sense. Because you're an engineer, you have a logic reaction against mass because mass is all virtual. Okay, it's nothing real, right? But again, you're going to kind of crystallize how the mass becomes real thing in this class, I hope. So I'm with you. I used to have huge allergic reaction against mathematical things, but I hope this class is going to change your mindset. Mass is your friend. You're actually going to create something real out of mass. Okay? So that's going to be project 2A to B. Draw streamline using MATLAB. Can we do such a thing? Wait a minute. It's 100% mathematics, but it's something real too. Because flow field is something real. Streamline is something you can see the actual flow field. Can you do it using MATLAB? That means 100% mass? Yeah. So that's where mass and the real physical thing meet up in this aerodynamics class. Okay? I hope you sense that. If you feel like, oh, mathematics, now my friend, it's a success of this class. Anyways. Differentiate with respect to alpha. What's alpha? Angle of attack. So you are going to differentiate with respect to alpha. So what are you doing here? Let's just do it. So you're actually doing this, okay? dd alpha of CMSC. This is going to be dd alpha of CL. And x over by AC minus 0.35 plus dd alpha of CM quote. Okay, so let's remember the definition of aerodynamic center. Somebody please remember definition.
It's independent of alpha.
Independent of alpha. That means if you take dd alpha of CMAC, what's this?
0.
This is going to be 0 because CMAC doesn't depend on alpha. Okay, so if you take a differential with respect to alpha, this is 0. That's the definition of the aerodynamic center. Now, we're going to define this thing, okay? This is something called DCL d alpha. We're going to call this CL alpha. If you start taking airplane control, flight mechanics, you're going to see lots of this kind of thing. CL alpha, CL beta, CL gamma, something like that, side, peak. Okay, well, anyways. So we are going to temporarily call this A0. Okay, we are going to define that. This is called lift curve slope. We ever heard of it? Very, very important. And also, we're going to define this, okay? DCM quota code D alpha, which is, this is actually CM quota code alpha. We are going to use actually M0, okay? We're going to define those terminology. One of them is lift curve slope. This is quota code moment curve slope.
That's little m, right?
Eh?
That's little m.
Little, which one is it, right?
Equal to your
M0, yeah, little M0. This is A0. Lift curve slope. Quota code moment curve slope. I'm running out of space, but anyways. So using those definitions, you can rewrite this equation. So this equation now becomes, okay, 0 equal to A0 x over by AC minus 0.25 plus M0, right? So from here, conclusion, location of aerodynamic center x over AC is equal to negative m0 over a0 plus 0.25. This is a conclusive equation. Location of aerodynamic center. Sorry, I'm running out of space. Go ahead.
And because the aerodynamic center is almost always quarter code, does that mean that M0 is approximately 0?
M0 is very small. You can expect that. Yes, that's correct. And then, as a matter of fact, if it's a thin airfoil, it's 0. Actually, very close to 0. So first of all, let's understand what is the meaning of width curve slope and then moment curve slope to begin with. Okay, let's move on to the next page. Take a look at example. So next page example says, okay, determine the location of the aerodynamic center in percent code of NACA 23012 airfoil by looking at this data set. So you can say two data set. One of them is, of course, you want to find out what is the A0. This is the lift curve slope. Lift curve slope is, you can look at the left figure here. This is a plot of two things. Okay, one of them is this plot. This is a series of the same kind of plot. It's just a variation of Reynolds number. Okay, so they repeated the same kind of test with lots of different change of Reynolds number. Okay. So the data of the circle, square, diamond, triangle, those are essentially different Reynolds number. Those two are the same Reynolds number. One is the different roughness of the surface. Okay. So they simulated so the rough surface also, smooth surface versus rough surface, trying to see the difference on the boundary layer formation also. Now, anyways, so this is the plot. This is called lift curve plot. Okay. So this is the plot of angle of attack against lift coefficient. Okay. And one thing you noticed was it's almost linear, isn't it? It's a straight line. So if this is a straight line or linear function, you can determine the slope of this line. Is that correct? Yeah. So this is A0. So A0, like I said, by definition, this is how much CL is expected for the change of alpha, DCL, D alpha. This is lift curve slope. If it's a linear function, you can determine by choosing two locations of CL, two locations of alpha, assuming those are straight lines. Somebody was raising a hand. Go ahead.
Yes. My question was, you said that line represents the lift core project?
Lift curve.
Lift.
Let's say lift curve. Any other question?
I got it. I think it's, does that say DCL D alpha?
DCL D alpha, that's A0. That's the slope of this line.
Yeah.
Is this a straight line? Almost, yeah. Let's assume it's a straight line. If so, this is called lift curve slope. It's actually, if it's thin airfoil, A0 is equal to 2 pi. The unit is inverse of radian. Can you convert it to degree? 0.11 per degree, either way. So this is A0 almost always, regardless of your airfoil type. It's usually 2 pi. Now, if you're talking about thicker cross section, this is going to be slightly, curved up. So, well, it's hard to say now it's a straight line, but it's still fairly close to a straight line. So we assume that way, almost always, okay? And what about the other one? M0. M0 is, again, this is the plot of a quote-unquote moment coefficient against angle of attack. Do you think this is also a straight line? It's fairly flat, however, it's a straight line almost, right? So I'm going to change the color here. So M0 is a quote-unquote moment slope. So you're looking at this line. Assuming this is almost straight, what is the slope? M0. So M0 is how much change of quote-unquote moment is associated with the change of alpha. DCM quote-unquote d alpha. That is quote-unquote moment curve slope. Again, it's very flat means it's a very small value, isn't it? It's almost zero. Yeah, that's why, quote-unquote is almost always the aerodynamic center. Now, suppose if this thing starts to go down, starts to go more slope, if you introduce camber and thickness. Okay. So that actually changes the location of the aerodynamic center slightly forward, but it's not so much. Okay, so this is fairly thin cross section, right? NACA 23012, 5-digit, slightly cambered. Still, this is almost flat. So let's just finish this exercise. Okay, so we are going to read off the values. First of all, let's read off A0. A0, by definition, this is DCLD alpha. So let's assume this is a linear function, delta CL over delta alpha. So you're going to choose the two different locations of alpha. Let's say I'm going to choose 8 degrees of alpha and minus 8 degrees of alpha. You can choose any two locations, but the minus 8 degrees, you have, what is the CL? Somebody please read off.
About minus 0.7.
Minus 0.74. I got one. The minus 0.7 is fine. Good enough. I got minus 0.74. How about 8 degrees?
21.
Yeah, it's very close to 1. Not the point 1.
Higher one.
1. Okay. Close to 1. I got 0.99. That's okay. 1 is fine. So you are going to compute A0, which is 0.1081. The unit is per degree, isn't it? Because this is coefficient, unit rest. This is degree. Okay? Unit is per degree, inverse of degree. Now, what is M0? M0 is, once again, DCM quote-unquote D alpha, in which we are going to assume linear line, which is delta CM quote-unquote divided by delta alpha, which is, it's tough to read off the values. In other words, you are going to read off right here and right here over this scale. Be careful. Don't use this scale. This scale belongs to CL. This scale is CM quote-unquote. Be careful. Lots of people actually choose this scale. Don't do that. Don't do that. So look at your note. Give me values. So 8 degrees and minus 8 degrees. So minus 8 degrees, I would say, what's the value?
Minus 0.18.
Minus 0.02 I got. You got the similar value. How about 8 degrees? Slightly less negative, isn't it? Slightly less negative.
Minus 0.01.
Minus 0.01. Okay. So this is going to give you very small value, but anyway, 6.25 times 10 to minus 4, again, per degree. It's fairly close to 0 anyway, so that means, hey, aerodynamic center is very close to quote-unquote XAC over bar is minus M0 over A0 plus 0.25, which is minus M0 is 6.25 times 10 to the minus 4. A0 is 0.1081. Go ahead.
You just picked 8 degrees and minus 8 degrees as arbitrary points, yeah?
Yeah, you
Okay.
can choose any range suitable for your application.
Right.
Yeah. So in other words, between minus 8 to 8, I assume it's a straight line. Anyways, so if you compute this, you actually get 0.244. So this is 24.4% code location measured from leading edge. Okay. Is it same as if this is given already, This is aerodynamic center position is already given here as a data set. Is it close enough? Yeah. 0.244 I got. 0.241247-ish based on the Reynolds number. So this is actual measurement. This is compared against your computation, 24.4% code measured from leading edge. So this is the location of aerodynamic center, very close to cortical, but slightly shifted forward. Okay? Question?
When you look at the graph and it gives you the X bar, what is that? What's the Y bar?
Huh?
So where you circle
Ah.
over there? Yeah, what's the numbers on the right? Is that the vertical position?
Vertical position, yes.
Okay.
Yeah, that's right. Leading edge. Yeah, go ahead.
The 0.25 in the equation never changes, correct?
Yeah, it's a 1/4. Yeah, it's in the original equation. So again, next page, please look at yourself. This is applied mechanics. The meaning of why AC is chosen, not the center of pressure. So we are going to finish up Unit A5 today, and then Friday, we're going to jump right into Unit B2. But if you have any question about B1, which is YouTube lecture, please bring your questions to the class. We can spend some time going over that. It's all about mathematics. So if you know it, it's a done deal. Okay, so otherwise, we're going to get into Unit B2 on Friday. All right, have a good
Can
day.
you scroll up for a second? Or scroll down? Second.
Yep.
So.
Sorry.
No worries.
So for my code, I have it set up as in the beginning it asks you if you want to use SI or customary.
Yeah.
When you enter in.
I'm good, thank you.
Depending on